Welcome to the University of Arkansas Division of Agriculture Agroforestry site, which was started in 1999 in collaboration with the USDA Agricultural Research Service, or ARS unit in Ames, Iowa, with Dr. Tom Sauer, as well as with Dr. Dirk Phillips in the Animal Science Department here at the University of Arkansas, Andy Thomas with the University of Missouri, and Ben Runkle also with the University of Arkansas in the Biological and Ag Engineering Department, and Philip Owens with the USDA-ARS unit in Booneville, Arkansas. So today we're going to be illustrating how soils can be used as integrators for explaining some of the systems level responses, or more specifically, how soils can help link hydrology with soil nutrient variabilities to forage and tree growth and production, and ultimately animal response across this continuum. And so we started an experiment to try to identify how spatially variable landscape attributes can influence preferential grazing in silvopastures. And silvopastures are the integration of agroforestry and animal production under one system, which can be a mechanism to mitigate risk, because you have an annual source of revenue from beef or hay sales, with trees providing a more long-term source of revenue. And so we outfitted cattle with these GPS tracking devices. And so when their heads are down and they're grazing greater than 70% of the time, within 15-minute intervals, a GPS coordinate is collected. And at the end of a grazing season, you end up with a grazing density map that looks like this. And so these green dots indicate grazing pressure, spatially and temporally. And then we collaborate with digital soil mappers such as Philip Owens to help develop digital soil property maps for things like soil nutrients, as well as soil depth. So these blue areas indicate deeper and wetter soils across this landscape. And so this translates into nutrients either concentrating or shedding, and ultimately reductions in forage growth and quality, and then reductions in grazing pressure. As you can see here, there are some linkages. And so ultimately we're seeing some correlations between soils, plants, and animals across the landscape. And so really digital soil mapping can help explain some of the biological processes that we see in the field.
My name is Philip Owens. I'm the research leader at the Dale Bumpers Small Farms Research Center in Booneville, Arkansas, where our mission is to find economic solutions for smallholder farmers. Increasingly, agriculture is becoming data intensive, both at large and small scales. One of the missions that our research group is focused on is improving the soil data and the resolution of soil data so that those layers can be used for integration within systems research.
The long-term goals of this project are to continue monitoring the changes in the microclimate, the accumulation of biomass over time. We changed the study recently where we've introduced some fertility treatments and reestablished the forage. And so we really want to see the effects of those treatments over time and how they affect tree growth and forage production.
The idea is, of course, by grazing animals in here, that we have a more resilient system to provide maybe in the future for producers or landowners in the area. And as Dr. Sauer pointed out already, we are interested in questions here, not just in regard to the trees, but also how can we keep animals or other crops in that system to provide a higher resilience in the future.
So now I want to set up the site to give you some background so you can understand some of the soils that we're dealing with at this location. If you look to the south, you'll see the Fayetteville Shale Formation. It is an interbedded sandstone shale formation that yields soils that are sandy to clayey. And then between the Fayetteville Shale and the Springfield Plateau, which is the Boone Formation, you will see a fault that separates the two areas. So we're nicely up on the Springfield Plateau and the Boone Formation. We wanted to show you a pit that is adjacent to the silvopasture site, and this is a pickwick. It's mapped as a pickwick, which is a fine silty, mixed, semi-active, typic paleodolt. We're looking at the profile. We have an AP horizon. Originally we would have an E horizon, but it's been plowed, so we have an AP horizon, a BT1, BT2, BT3, BT4. We have silt loam in the surface, slightly darkened by organic matter, and then we go into silty clay loams in the subsoil. To start the mapping, we had a 2-meter digital elevation model created with LiDAR, and we downsampled that 2-meter LiDAR data to 10 meters. And that helps when we're doing the statistical correlations to relate landscape features to soil properties. We ran some terrain attributes such as topographic wetness index, multi-resolution ridge top flatness, valley bottom flatness, slope, curvature, about 20 different terrain attributes. And so what we're trying to do is correlate that to points. We created a stratified sampling method based off of landscape topography. Rather than a grid, which can cause oversampling or undersampling of places in the field, we tried to get and target all known differences within the field. We focused one of our research projects on this agroforestry site that's been explained to you. It's a fairly small area, but it has some differences within soils. And those differences are terrain driven, and we want to use the metrics of terrain and the soil relationship that relates to hydrology to try to understand how water differences and soil differences are influences responses.